This demo store looks ready to ship. The buttons work, the dashboard looks clean, and the tests are green. But a signed-in user can ask for an order that is not theirs. Pause here. Would you fix the screen, hide the order number, or make the server prove ownership before it returns anything? In this video, we will secure the fictional ShopBoard app using 5 checks you can reuse in any stack. We will protect object access, strengthen sessions, keep data separate from executable instructions, remove unsafe defaults, and keep third-party code accountable. Every action stays inside a local simulation with invented users and records. Think of the application as a chain of trust decisions. The browser can make a request, but it cannot grant itself permission. The server decides whether an identity may perform an action. The data store receives structured, authorized work. Security gets simpler when every boundary has one explicit question and one default answer: deny until allowed. Our lab is a realistic simulation, not a real target. ShopBoard runs only on localhost. Maya and Noah are fictional users, and every order is made up. We will compare one allowed action with one blocked action. There is no scanning, automation, credential testing, or reusable exploit sequence. The point is to see the control, the correction, and the verification clearly. Pause and pick one. Hiding an identifier only changes what the screen displays. Requiring a session tells us Maya is authenticated, not what she may access. The useful answer is C. The server checks that the requested order belongs to the current user before it returns the record. Authentication and authorization are related, but they are not the same decision. Here is the simulated result. Maya opens her own invented order successfully. Then the same local application asks for Noah's sample order. The unsafe version returns it because the server checks only that a user is signed in. The issue is not the format of an identifier. The issue is a missing server-side relationship check between the current user and the requested object. The correction is small but architectural. The server takes the authenticated user from trusted session context, then retrieves an order only when the order identifier and owner match. If that relationship is absent, it returns a safe denial. Retest 2 paths. Maya can still view Maya's order, and Maya cannot view Noah's. That positive and negative pair is evidence that the rule now works. Now move from ownership to identity. A session is not a single login form. It begins at enrollment, continues through authentication, and changes when a user resets a password, gains a new role, or signs out. If we protect only the first screen, the rest of the lifecycle can quietly weaken the identity decision we thought we had made. Here is the next pause point. A password reset changes trust. The strongest answer is B. Rotate or revoke active sessions as appropriate and ask the user to sign in again. A color change has no security value. Keeping every old session makes a recovery event less meaningful. Your framework may provide the primitives, but your application still needs an explicit lifecycle decision. In the local simulation, a user can browse their own orders with a normal session. But changing the account email is a higher impact action. The application asks for recent authentication, uses appropriately protected session cookies, and records the outcome without storing reusable secrets in logs. Security is not one giant wall. It is a set of proportionate checks around the decisions that matter most. Next is a rule that applies far beyond one database. User-controlled text is data. It should not become part of a database query, command, template, or browser document by string assembly. Use structured interfaces that keep code and values in separate slots. Validate shape and intent, but remember validation alone does not replace authorization or safe data code separation. In our whiteboard code card, the unsafe pattern mixes application text and a value into the same instruction. The safer pattern uses a parameterized query interface, binds the requested value separately, and includes the current owner in the lookup. The browser gets only the permitted response. This is easier to review because the security rule is visible exactly where the record is selected. The local API receives a malformed checkout request. The secure behavior is boring: reject the unexpected shape, return a concise client-safe message, and store a correlated internal event for developers. It does not echo secrets, expose framework details, or continue in an invalid state. Handling errors well is a security control because real systems fail at boundaries, timeouts, retries, and bad input. Security misconfiguration is often not dramatic. A debug route gets left on. A permissive cross-origin policy survives from a prototype. A test credential appears in a config file. The fix is a deployment habit. Define production-safe defaults, review the differences between environments, keep secrets out of source code, and make insecure toggles visible enough to fail a release review. In ShopBoard, the release checklist shows that debug mode is off, the allowed origin list is intentional, and secret placeholders are resolved only at runtime. The simulated deployment refuses to continue when a required setting is missing. That is better than silently guessing. A secure configuration should be both reviewable by humans and testable by the delivery process. Modern applications are supply chains. Your code depends on packages, build systems, registries, runners, repositories, and the identities that publish releases. A clean code review cannot guarantee that every part of that chain is safe. Start with an inventory, minimize unnecessary dependencies, use trusted sources, and preserve the ability to patch or replace a component quickly. A local inventory flags a fictional package update. The team does not blindly bump every version or ignore the alert. They confirm the component is present, understand whether the affected code path is used, consider exposure, update through the approved source, and test the application. This turns a noisy dependency list into a controlled engineering decision with evidence. The next check happens before implementation. Consider a refund workflow. Even flawless code is unsafe if any support account can issue unlimited refunds with no approval, rate limit, or audit trail. Draw the asset, the actors, the trust changes, and the abuse path. Then turn the drawing into requirements such as amount limits, separation of duties, and reviewable events. Pause for the third check. A legitimate account can still perform an unsafe action if the design has no guardrails. The answer is B. Put the amount limit and second approval on the server-side workflow. A longer password and a hidden button do not create a business control. Threat modeling helps us distinguish identity problems from missing design constraints. In our simulated refund event, the log records the actor, the requested amount category, the outcome, a time, and a correlation identifier. It does not record a password, session token, or payment secret. Good logging supports detection and response without creating a second data leak. Decide which security events matter, protect the records, test alerts, and make an owner responsible for the response. Finally, test the edges. What happens when a dependency times out, the same checkout message arrives twice, or an expected service is unavailable? A safe system validates early, uses idempotency for important repeatable actions, limits resource use, and returns a controlled result rather than silently succeeding or leaking details. Reliability controls and security controls often reinforce each other. Bring the checks together in a release gate. Test authorization with both allowed and blocked examples. Test session changes around recovery and sensitive actions. Test that malformed input fails safely. Assert production configuration, review dependencies, and preserve the results. This does not promise perfect security. It gives the team a repeatable way to make fewer assumptions and catch important gaps before users do. Here is the practical next step. Choose one high-value endpoint in an application you own or are authorized to assess. Write its expected rule in one sentence. Create one allowed test and one blocked test. Check the server-side control, not just the interface. Then record the result. That simple loop becomes the foundation for stronger application security over time. Remember the 5 checks. Authorize important requests. Treat sessions as a lifecycle. Keep data separate from code. Ship safe configuration and accountable dependencies. Design limits for sensitive workflows and log the decisions you may need to investigate. CipherVibe turns these ideas into practical labs and clear diagrams, so subscribe for the next secure build walkthrough.